So now that I've found some of the mathematics behind critically damped and underdamped, I want to try to see if I can find out exactly what would happen in the critically damped case in particular, and just see if we can come up with some examples in general. So I'm going to start with this equation of what R would be calculated to be. And we're going to imagine a situation where, say, we had a spring of spring constant 1 Newton per meter, a mass of, say, 1 kilogram, and, well, we want the critically damped case. So we'll say b squared minus 4mk equals 0, which means b squared equals 4, or b equals 2. Now 2 would be the kind of the velocity coefficient of friction. It would be 2 newtons per meter per second. So some kind of viscosity that slows the mass down. So this comes from the Newton's law. The sum of forces is mass times acceleration. So we would basically have the negative kx coming from the spring minus bv coming from the velocity of the mass equals m times a. And so it's going to be the spring constant is negative x minus 2v equals the mass times acceleration. And these can each be written as a derivative of x in time. So the velocity is the first derivative of x, so x prime equals m times x double prime, the second derivative of the position. And we decided arbitrarily that that mass would also be 1 kilogram. And we put all of this together on one side to have basically x double prime plus 2x prime plus x equals 0. And we assume that x of t takes the form basically e to the rt. And r in this case was, well, b squared minus 4mk was 0, so it's just going to be negative b over 2m. R is negative b over 2m, and b is 2, and m is 1, so it's negative 2 over 2, so it's just equal to negative 1. So this is the case where x of t equals e to the negative t. Actually, let me call that x1 of t, and I'm going to also tell you, take this as a matter of trust or faith, as you may like to call it. x2 of t is e to the negative t, and I'm going to show you that if that any equation of the form of this form will satisfy this equation, and any equation of any function of this form will also satisfy this function. And this is actually kind of an unusual case that we can introduce this t variable here, and it has to do with that what's basically called a double root of the of this characteristic equation. So let's first look at something of the form a e to the negative t. If I say x of t is a e to the negative t, then x prime of t is equal to negative a e to the negative t, and x double prime of t is equal to positive a e to the negative t. Basically, whatever is in front of the exponent here pops out, so the negative 1 pops out here, and the negative 1 pops out here. And you can quickly verify that this x double prime would be let me just write it in red here. A e to the negative t plus 2 times negative a e to the negative t plus a e to the negative t would end up being 0. Okay, for this second equation, let's verify that it also would satisfy this relationship. If I took, well, we've got it written here, x2 of t equals te to the negative t. I'm just going to go ahead and multiply that by some constant b te to the negative t. And now the first derivative, we're going to use the product rule here. So we take, so the first derivative, x2 prime, is b times, okay, this times the derivative of this would be negative t e to the negative t, plus this times the derivative of this would be just plus e to the negative t. And then we'll take the second derivative, x2 double prime, which is going to be b times, again, use the chain rule, which is going to be the first thing times the derivative of the second thing, which would be negative t, positive t e to the negative t, plus, or just minus this time, minus e to the negative t, and then we'll take minus the derivative of that, or plus the derivative of that, which is minus e to the negative t, or in total it is b times t e to the negative t minus 2e to the negative t. So what is x double prime plus 2x prime plus x would be equal to x2 double prime is b t e to the negative t minus 2e to the negative t plus 2 times x prime, 2 times negative t e to the negative t plus e to the negative t plus our x, which is going to give us plus t e to the negative t. Now I'll combine like terms. We've got the t e to the negative t minus 2t e to the negative t plus t e to the negative t comes out to be 0. And then we have the negative 2e to the negative t plus 2e to the negative t also comes out to be 0. So that means that any function x of t of the form a plus bt times e to the negative t is going to satisfy the differential equation. It's going to satisfy Newton's second law of motion. More generally, that's a plus bt e to the negative b over 2m t. And that happens if b squared equals 4mk. That is the critically damped case. So that means you can choose a spring constant, or you can design your spring so that based on the viscosity of the fluid and the mass of the say the car or whatever, in order to get at this critically damped situation, so you minimize the amount of bouncing in the system.